Good morning, everyone. On behalf of the Global Sustainable Electricity Partnership, GSEP, we would like to welcome you to the Second Life Batteries Enabling Sustainability for Electric Mobility webinar. The GSEP is an organization of leading global electricity companies that promotes electrification and sustainable energy development. Through its webinars, the GSEP showcases valuable educational resources to learn more about new technologies and international best practices in sustainable energy and electrification. Today, the GSEP members will present the results of the Storage Technological Community. The community is composed of a group of experts from GSEP member companies. The results will be presented by the following experts: Mr. Pasquale Salsa, Head of Long Duration Storage and Hybrid Systems at Enel Global Power Generation. Mr. Salsa is an energy engineer with 10 years of experience in the energy sector. He leads the innovation team focus of energy storage, hybrid systems, and hydrogen. And Dr. Kamyab Amouzekbar, Senior Researcher at Hydro-Québec. Dr. Amouzekbar works at Hydro-Québec Center of Excellence in Transportation, Electrification, and Energy Storage. He has more than 25 years of experience in research and development, scale-up and commercial operation of electrochemical processes. The main focus of his current activities is the development of lithium battery materials, as well as the recycling of lithium batteries. Prior to starting the webinar, I would like to provide technical instructions. Language. Interpretation to French and Spanish is offered. Please select your language at the bottom of your screen. Presentation slides. The translated slides, English, French, and Spanish, can be found on the link that has been shared on the chat section. Questions. If you have any questions, please use the chat box to send them to the speakers. Please note that your questions will be answered at the end of the presentation. I will now pass the floor to Mr. Salsa to start the presentation.
Thank you, Luis, and hello, everybody. It's a pleasure for me to be here. So hopefully you will find interesting this webinar. And I think we can start with an introduction on what we are talking about with the second life batteries. So please, Luis, if you can go to the first slide. Okay, yeah, this webinar is based on an activity that was made by a working group inside the Global Sustainability Electricity Partnership, a technical community on energy storage. So it's made with the contribution of all the names and the companies that are presented here: Enel, Kansai, ONE, SGCC, AEP, and Hydro-Québec. This is more or less the agenda, the topics that we are going to cover in this 1 hour of webinar. We will start with a quick introduction, then there will be what we are talking about with second life batteries, what are the enabling factors and the limits of second life batteries, what are the economics, the volumes in place, and then, in particular, my colleague Kamyab, we will give you some hints about the sustainability and the circularity aspect of the second life batteries, and more in general, the end-of-life management of the lithium batteries. And then we will talk about some cross-sector synergies that we find during our activities. Okay, I think we can start going in detail with the first topics. So what we mean with second life batteries. Okay, basically, when an electric vehicle that uses lithium batteries reaches its first useful life, that means having whenever you use a lithium battery, it lost a part of its capacity every time I charge and discharge the battery. This is an effect that typically we can see and that we are aware when talking about mobile phone, for example. At the end, the chemical, the technology that is inside our mobile phone is similar to the one that we have in cars. When the capacity reaches a level that is not enough to to keep the required standard, in particular in terms of capacity. That means number of kilometers that I can do with a single discharge, and also the other effects, like for example, the self-discharging. We say that the battery inside the vehicle reaches its end of life. And because it's not enough to give the required comfort to the car driver, basically, to the car owner. So at this point, we have various alternatives. We can simply dispose of the battery. That is, let's say, the easiest things to do, but also the worst thing from a certain point of view. And it indeed is something that cannot be done in many regulations in many countries. We can directly recycle the battery, and we will see in the next slide, in particular with Kamiab, what are the options, the possibilities that we have to recycle not only lithium batteries, but also the other, not only the lithium that is present in lithium batteries, but also the other chemicals that are present as well in the lithium batteries, for example, cobalt and nickel. But there is also another option that is not a real option, but more an additional step that we can do before recycling, that is reusing the batteries in other applications. And this is the focus on what we are speaking today. So using first life batteries that reached the end of their first life in a second application. And I think we can go on. Luis, please. Okay, so we have various options to reuse batteries that were meant to work on electric vehicles. Basically, when a battery pack reaches its end of life, the repurposing approach is means that we will take the battery pack from the car, so we dismantle the battery pack, but without dismantling the single cells that are included in a pack. You have to think a battery pack like a number of cells, very similar to the ones that you have in your phones, that are assembled in serials in parallel to reach the required levels of voltages and current. So in a repurposing approach, you don't take the single cells that are composing the overall package, but you just use the pack as it is in second life application. We will see that this is an interesting approach, maybe the best approach, but nevertheless has some steps to do before you can use a pack that was not meant to be used in a stationary application to make it work on a completely different environment than the one for that it was designed to. The refurbishing approach instead goes more in detail in the dismantling process, because it doesn't only take the complete pack that is included in an electric vehicle car, but it opens the pack, select the single cells, collect according to the characteristics, take the cells to build a completely new pack, and then this new pack made of single cells selected from the original pack are assembled and used in a new pack that can be used in a stationary application. There is also another concept that is the remanufacturing. That means using the single cells that are composing the battery pack, selected, repaired, and restored to be used again in a new battery electric vehicle application. This is out of scope because it's an approach that is not, let's say, particularly interesting from the technical economic point of view, because basically doesn't use completely doesn't optimize, let's say, the usage of the cells that are still suitable, that are in the sense that still have some juice to be extracted. We can go on. Okay, so comparing the two different approaches, refurbishing and repurposing of the battery packs, both of them has pros and cons. Refurbishing the electric vehicle battery, the battery pack, let's say, it's not an easy operation, because you have to open a pack that is sealed. So there is a risk of, first of all, there is a risk of damaging the pack itself, and more importantly, the cells that are included in the pack. So basically, it requires a lot of time and specific know-how to do this kind of process in a safe approach and not risking of damaging the single cells and so not being able to reuse them in an additional approach. On the contrary, it has some advantages because once you have selected the single cells that are still working, that still has a proper autonomy inside the single pack, you can use them to build a pack that at the end is like a new first life pack. So you, at that point, you don't need any specific, let's say, attention to use this new pack in a stationary application. But it's a process that overall is quite expensive, risky, and doesn't optimize the whole value chain. On the contrary, the repurposing approach, it's a more plug and play approach because using the entire pack reduce the risk of damaging. It's more safe because basically you have you don't have any risky operation also from the operators, and you can use the original battery management system. That is the lower level system that manages current and voltages at the cell levels. That can be that is the most important system also to warranty the performances, but also the safety of the pack when it will be used in a second life approach. So basically, with this approach, it's possible to use the lower level control system as it was designed. On the contrary, there are other limitations that can be overcome, and we will see also how they will be overcome. First of all, you need a higher level of control system, a so-called master BMS, that make it possible to communicate with the single BMS of the packs with, let's say, a higher level control system that manages all these battery packs that were not meant to work together and to communicate with the overall power conversion system that is able to connect the battery packs towards the grid. Other limits are more, let's say, technical in the sense that typically the voltage of the single packs is lower than the typical voltage that is used on a stationary application. And from a certification point of view, typically these kind of packs are not meant to be connected in series. That means that to reach the required level of voltage, or in any case, to make them work with standard power converter system, standard inverters, you need or to add DC-DC converters to match the voltages of the packs with the one with the inverters, or you need to have inverters, PCS, that works at lower voltages, and it's more expensive because with the same power, working with lower voltages means having larger equipment, basically. And of course, there is a topic of guarantees because, of course, the system integrator will not be able to guarantee performances of the batteries, but it's something that must be done by the original manufacturer that somehow that must give to the final user a warranty in terms of residual capacity or residual performances of the second life batteries. I think we can go on. Okay, as a technical community inside the GSEP, we had some experience that was shared among the various members of the community. For example, this is a project that is done by Enel, the company for which I work. Is a project that we did in Melilla. Melilla is a Spanish city in Morocco. It's an insulated electrical system, so it's like an island from the electrical point of view. So the need for a storage was required because we needed a storage system to make the conventional generator work with more flexibility to let them be able to follow variations due to the increasing level of penetration of renewables and the fluctuation in load. So given this this need to add the storage system to the electrical system, we took the opportunity to use not a conventional storage system, but to do a second life system in a real what we call a real life lab. So basically an application that has already, let's say, that is already done in an industrial environment. So we are building, we built a project made with Nissan Leaf Second Life batteries that were assembled up to reaching a capacity of 4 megawatt, almost 2 megawatt-hour. We can go on. Okay, so basically, of course, this project, let's say, has a lot of value that is not only technical. Of course, with this project will give us a lot of important information, in particular on the performances of the residual performances of these second life batteries. That is somehow something that is still unknown, in the sense that we know what is the residual capacity of a second life batteries, but we cannot say in detail how this residual capacity will be affected by the future operation. So for sure, this will be a significant step towards the knowledge that we can have in second life batteries in real operation. The project gave us a lot of experience also, not only in the operation and maintenance phase, but also during the execution of the system, during the engineering, the engineerization of the system, because a lot of specific actions and let's say solutions were developed in order to make the second life modules work in a completely different industrial and technical scenario. Then, of course, is very different from a car. We are talking about an industrial system connected to a grid. And of course, it has also some strategic rationale that is more or less, let's say, completely driven by the need for sustainability. That is a fundamental aspect along the value chain of lithium batteries. Let's say that this is an important step towards having a circular approach in using lithium batteries. We can go on. Okay, here you can find some pictures during the construction of the system. As you say, the batteries are on the right of the picture, are assembled in racks made designed specifically for this project. We together with their DC bus and all the electronics and control system, and then are assembled in a facility that, as you can see, is by far different from a car. So the battery is the same, but the scenario and the application is completely different. Okay, here are some other details. As you can see, the packs are exactly like the ones that are inside the electric vehicle. There is an interesting topic that I forgot to mention. We are using here at the same time second life batteries and first life batteries, both of them let's say from auto vehicles, in order to assess the different performances that second life and first life batteries will have during the operation. Okay, other interesting applications were made by our colleagues from Jiangsu S. They used second life batteries in a couple of applications, both applied to telecom towers, replacing the typical solution that was relying on lead acid batteries, and of course has much worse performances during the operation. And another application is on, let's say, still on a lower scale, but very distributed, and is let's say a kind of micro battery used in distributed power stations. And here you can find some pictures again that were made by our Jiangsu ES colleague. Okay, let's go on. So let's see more in detail what are the batteries and how they can be overcome. Okay, basically just summarizing, what are the batteries? The barriers that make second life batteries still hard to be, let's say, developed as a real market, and what are the solutions that can overcome these barriers? Basically, from the technical point of view, there are still uncertainties, and let's say that for a first of a kind system, like for example the one that we did in Melilla, a lot of things were to be done from scratch. So there was not, let's say, a standardization regarding test protocol, KPIs, guidelines for system integration. Of course, this is something that project after project can be, let's say, reused, and the know-how can be used as a starting point for future projects. So we are quite confident that the more second life projects, the more system integrators are getting confidence with this integration problem, the more solution will be present, and so also the economics of the projects will take advantage of the experience that we are doing. Other barriers are related to the lack of experience, as I said before, about the performance of second life batteries. So for sure, having this kind of first demos, like the ones that we are doing, and also Chinese colleagues are doing, will make available a lot of data that will be really important, in particular to understand how the performance degrades, because an important topic is how capacity is affected, in particular at the end of the residual capacity. When a battery reaches a residual capacity that is lower than the 80–70% of the original value, there are still uncertainty about the behavior of the further degradation. And of course, there are economic uncertainties because, let's say, we still have to define better a standardized approach. So if the first projects are made, let's say, are completely customized, of course, the economics are more difficult than starting with a standard project with Versa-Life batteries that is very well known by system integrators and by the actors of the value chain. We can go on. Yes, just to give you some more ideas about these technical challenges. Consider that in terms of design, there is a huge number of different designs for the battery packs. There is this estimation that by 2025 there will be more than 250 new kind of electric vehicle models with batteries that are manufactured by about 15 manufacturers, so each one with its own design and its specification. There is a topic that is the falling cost of lithium batteries, of first life lithium batteries. That is something that second life batteries has to take into account, because they must be for sure cheaper overall, not just the module itself, but also all the integration, because otherwise, if they are not competitive with first life batteries, one can use first life batteries for sure for new projects. There are no specific warranties, and in particular no specific standards for battery management system, and let's say the state of health, that is a parameter that gives you an information about how healthy is a battery when it reaches the end of its first life. So for sure, it's quite hard to access in a standardized way on the information from that are stored inside the control system of an electric vehicle battery. So standards are required to make it easier for system integrators to assess the performances of batteries that have reached the end of their first life. And there is still no, let's say, market-wide standards in terms of policy of regulation, even if something, as we will see, is moving. So hopefully it's something that is going to be addressed soon, at least starting from some of the countries of interest. We can go on. Okay, nevertheless, apart from, let's say, the barriers, that are also some leverages, let's say, that can that we must take into account to see the value of second life batteries. For sure, there is a value related to the circularity of their contribution in the value chain, because using second life batteries means reducing the amount of waste, and let's say more specifically, having a greater value of the raw materials that are used in the supply chain of lithium batteries. When we talk about lithium batteries, we are not talking just about lithium, but also about cobalt, nickel, that are quite critical in terms of how they are extracted, in terms of the also the geopolitical situation of the countries that in which these metals are more common. So let's say that using second life batteries means extracting more kilowatt hour for the same gram or kilogram of material. So for sure, it's something that give value from the circularity point of view of the battery value chain. Most of the problems in terms of standardization of BMS, of design, can be overcome if electric vehicle manufacturer have this, let's say, circularity by design approach. So if the battery is designed from the origin as something that that can be used not only in the electric vehicle, but also in a stationary application, and that at the end of the life can be recycled, everything, it's easier for the, let's say, the various technical players that will manage the battery when it's out of the car. And of course, a market can be enabled, let's say, because at the end, what is now seen as a cost, not typically, so something that must be dismantled, that must be recycled and so managed, can be a value, because it's something that can be put again on the market when it reaches its end of life. And again, a good contribution that can go in the direction of second life market are standards of all of kind. Let's say standards of BMS and how the information are stored inside the battery, standards related to the possibility of using battery packs not only one by one, but also connected in series. So if there's a standardization will come, everything will be easier for who is interested in this kind of applications. We can go on. Okay, yeah, this is an highlight from the European Union that is that has a new regulation for batteries that is in scratch, let's say in draft, so it's something that is in development, but it's quite interesting because it starts, let's say, giving a real role in second life batteries. So for the first time, is putting some pillar that will help rising this market, or let's say these applications of for second life batteries. Is something that let's say is being proposed by the end of the last year. So hopefully it's something that in the next year will be executed, and could help this kind of applications. There is a link, so it's public available. Okay, of course, also the choosing the right application for the right battery is something that is important. When we talk about storage, we have two kind of let's say two families of application: the power intensive, so the one in which let's say a lot of power is required, and so a lot of current is extracted for the battery. The other family is the energy intensive application that are, let's say, more related to lower charging and discharging cycle. Both of them has advantages and disadvantages when we talk about second life batteries. Power intensive applications are interesting because typically second life batteries, or better, the first life batteries that were designed for a vehicle have the capacity to give a lot of current, because typically are used in applications like electric vehicles that sometimes need a lot of current, so they they can be competitive with first life batteries that are not designed to do such kind of application. On the contrary, energy intensive application can can give a lower stress to a battery that is already have done a lot of cycles, and so somehow can extend their life. So of course, evaluation must be done case by case, and for sure, say having some data from the field, for example, from the first demo that we were looking at, will give some hint also in selecting the right application for second life batteries, also according to their residual state of health and the residual capacity. Okay, just some words about what are the expected volumes of second life batteries, and some note about the cost. About the volumes, let's say, long story short, there will be a lot of second life batteries in the next years, because let's say that the stationary application will be a fraction of the volumes of batteries that will be used for electric vehicle applications. So for sure, what will drive the market is electric vehicle, not stationary storage. So there will be a lot of let's say, of batteries that will reach their end of life. In particular, let's say, as you can see from various scenarios, after the 2025, that will be available and that will be potentially used in stationary application. Is estimated to have almost 200 gigawatt-hour of second life batteries that are reaching their end of life, or end of first life, by 2030. And we can go on. About the cost, let's say that the scenarios are various. More or less, let's say a good approximation is that in terms of capex, second life battery can be cheaper than first life batteries, also considering the decrease in price that first life lithium batteries will have towards the 2030. Of course, everything taking into account everything, not only, let's say, the cost of the pack, but also, let's say, the residual performances. Regarding the two approaches in the reuse of batteries, repurposing and refurbishing, as we discussed, the repurposing, so that is the direct use of the pack as it is without dismantling, is always the let's say, the preferred approach in terms of cost. And here is another confirmation, let's say, because if we break out the cost, and there is an interesting tool made by Enel for the, let's say, the calculation of the breakout of the cost of the second life battery, let's say that 32% of the cost can be, let's say, avoided if I use directly the battery pack instead of dismantling and selecting the single cell like in the refurbished approach. Okay, I leave the microphone to Camilla for sustainability and circularity.
Great, thank you, Pasquale. Good morning and good afternoon, everyone, I guess, depending on where you are. Thanks also, Luis, for the nice introduction. As Pasquale mentioned at the beginning of the webinar, actually, the state of health is one of the main criteria that determines where the battery is it is situated in its overall life cycle. The value of 80% that Pasquale mentioned is considered to be when the battery has reach its first life, end of its first life, and then we go to second life applications, mainly stationary applications. And obviously, I think we went too far. Yeah, sorry, I just wanted to make the introduction. Could you go back to the first one, please, Luis? Yeah. And the consensus is that now that when it reaches a state of health of around 50%, so its direct capacity utilization is around 50%, then we can consider that the battery has reached its end of life and it should be directed towards recycling. So that's what the section that I will be talking about. We will talk about the drivers and challenges of recycling batteries. We will be talking about the recycling options and technologies and some policy implications. Next, please. Yeah, so this is a list of, obviously not exhaustive, of the most important economic and environmental drivers for recycling. These drivers, to some extent, are similar to the drivers for the second life application. If you consider the actually the fact that the batteries can contain a lot of flammable materials, some transition metals that are considered toxic. One of the main drivers would be the fact that it alleviates the contamination risk and also the hazards. Also, considering the fact that the 30 to 50% of the greenhouse gas emissions for the electric vehicle is mainly related to the fabrication of the battery, the recycling would allow to reduce the carbon footprint of this manufacturing. Also, there are some estimates that the use of recycled material would allow to decrease by around 30% the cost of the manufacturing of the batteries. And the lithium, I mean, overall, actually, the electrical vehicles have a much greater reliance on minerals compared to the and conventional internal combustion engine, mainly cobalt, nickel, manganese, and lithium. So the use of recycled material will allow to reduce the reliance on this mineral extraction operations. And also, in some cases, actually, some specific suppliers that we would like to avoid, either because of some ethical issues, it could be sourcing from conflict zones, or it could be to some strategic reasons. It will allow us to have the concept of having an urban mine and being able to source from different suppliers. And then I would say also the high cost of transportation of the used batteries actually is another incentive to have local recycling infrastructures, and that would actually be economically important to create some jobs in countries that currently they are not actually benefiting from any battery-related industry. Next, please. So among the technical and financial challenges for the recycling, I would say the quality of the product is one of the main criteria. Actually, in fact, the recycled material, in order to be used in the synthesis of cathode materials and be used by the battery manufacturers, it has to meet all the required technical specifications by these manufacturers. If that is not the case, then it can be directed towards lower value and lower purity applications. For example, nickel can be directed towards the synthesis, the fabrication of stainless steel. Aluminum and lithium could be actually used in the fabrication of cement. And if none of these even lower qualifications are met, then it might be going towards recovery or something that we would like to avoid, which is the waste and landfill. Other important challenges are also the fact that the reliability of being a supplier as a recycler, that's a very important criteria for battery manufacturers. And obviously, down the road, the cost is being cost competitive on the entire value chain after recycling regarding collection, transportation, and all the processing costs. And obviously, having a low environmental footprint and being environmentally friendly is a very important factor. Next, please. So I would say the current, to talk about the current state of the recycling technologies, they can be grouped in three main categories: pyrometallurgy, hydrometallurgy, and direct recycling. The pyrometallurgical processes actually treat the batteries at a very high temperature, around 1500 degrees Celsius. And it's based on smelting and actually burning all the carbon-based material. And they end up having all the valuable metals such as nickel, cobalt, or manganese in the form of an alloy, actually, that need to be treated later on. Hydrometallurgical processes are based on using usually an acid solution to dissolve the active material. So it could be a complete dissolution or a partial and selective. And then extractive processes are used to recover all these important materials. The direct recycling is based actually is aims to restore the initial properties of the battery without actually decomposing it into its subsequent elements. Next, please. So this is actually a table. I won't go through all of them, but it's summarizing some of the advantages and disadvantages of each approach. In the case of the pyrometallurgical approach, it's a very flexible process. It can handle any type of batteries. There is no sorting or mechanical treatment needed. There is no need for crushing or size reduction. And they are one of the first approaches to be used. So they represent actually a proven technology. But the disadvantages are mainly the fact that they are very energy and capital intensive. And there is a lot of actually gas emissions that need actually the installation of expensive and I would say complicated gas recovery equipment. And some of the main important components such as lithium, aluminum, or even the electrolytes and organics are not recovered in this process. Hydrometallurgical approaches, on the contrary, are quite energy efficient. There is practically no air emissions, and they're actually capable of recovering materials such as lithium, which is at this time not the case for the pyrometallurgical approaches. But as disadvantage, we can mention that there is need for the pre-treatment, discharging, sorting, size reduction, and then there is a high volume of effluents actually that are produced and need to be disposed of and treated, and they usually have higher operating costs. In the case of direct recycling, the advantage is that the cathode structure retains its properties, and there are actually other components that can be recovered easily with this method, and they are energy efficient. However, as a disadvantage, we should remember that to this day, actually, none of the current approaches have been able to recover completely the initial properties of the cathode material. And also, there is a good chance that the restored cathode material, by the time it is recycled, might be obsolete. We should remember that the batteries that we recycle today actually were introduced in the market maybe 10 or 15 years ago, actually. Could we go to the next, please? So in terms of policy implications, the priorities for policymakers that are aiming at accelerating investment and development of recycling processes, they can be actually grouped in three main categories of market creation, R&D priorities, and pilot projects and process scale-up. In terms of market creation, one of the main important barriers for the development of recycling batteries is the lack of regulatory incentives, actually. The measures that could be considered for the market creations are mainly applying the extended producer responsibility regulation. This implies that actually the car manufacturers would be covering the cost of the collecting and recycling. This actually would be a very good incentive for them to add the design for recycling. Pasquale was talking about having the design for second life, and also I think it's an important to consider this from the very beginning at the manufacturing level, to have a design for recycling and for second life battery. And also it will actually be an incentive for them to have more collaboration with recyclers. Setting cost and performance goals with rewards and penalties in case of non-compliance, actually it's another measure. Like the US Department of Energy has programs setting prices for developing recycling processes that reach certain specific recovery rates, for example. Increasing gate fees for landfilling would help also to encourage the recycling. Establishing a scheme of deposit at the time of the purchase of the vehicle actually would be also something that could have some effect. With actually this deposit would be paid either by the consumer or by the car manufacturers, and would be actually refunded at the time of the collection. In terms of the R&D priorities, I would say it's important to consider the entire recycling value chain, whether it's the collecting, the transporting, sorting, all this have to be more, the R&D activities should have some more focus on these steps of the recycling, especially if one considers that the fact that the 40 to 50% of the overall recycling cost at this time, at least, is related to the transportation issues for the recycled batteries, because they're considered as hazardous waste, actually. And also it's important not to focus when we're developing recycling processes just to recover the cathode material. There are other components in the battery that need to be recovered. For example, the graphite anode is one of the most neglected one, or the recovery of the electrolyte. And as I mentioned, the design for the recycling and facilitating the disassembly is one of the things that should also be already considered in the development of the batteries. And also it's important to, as I mentioned, the quality specifications of this recycled material is a very important factor, whether it will be used by the manufacturers of the batteries or not. So it's important to already set and determine how to reach these, these quality specifications. Next one, please. And so regarding the third category of the policy priorities, we should consider that expanding R&D activities is a very highly desirable actually objective, but there are many existing solutions for recycling batteries at this time, and the policy priorities should support pilot studies that will allow to evaluate and demonstrate the technical and financial viability of these existing solutions also. The projects should involve actually all the stakeholders to participate, all companies from automotive, battery, transportation, regulators, scientific community, not just the recycling industry. And at the same time, we should remember that one of the biggest challenges that the recyclers are facing at this time is to have a secure supply of spent batteries, actually, to carry out these pilot studies. And actually, according to the industry, right now the capacity, the recycling capacity is actually underutilized, and these actually challenges can be mitigated a lot by increasing cooperation and communication during the all value chain. And actually, it's this part is a bit in contradiction with what we believe, that when the entire wave of batteries will come to the market, we believe that there would be a lack of capacity for recycling, but at this time that is not the case right now. So I would like to actually forward back the webinar to Pasquale, and I will be available for questions at the end of the presentation.
Yeah, let's say that one of the last activities that we did inside the working group, inside the technical community about storage in the GSEP, was identifying potential collaborations. And of course, what came natural was identifying what are the main electric vehicle associations. Also, because, and here is a map of the various associations that we identified around the world. So if we can go to the next slide, and let's say that for us that are utilities, no, so that are end user of batteries, it could be really interesting to have to start such a kind of dialogue, no, between with the electric vehicle world, because at the end, second life batteries can be the kind of point of contact between the two worlds. It could be interesting to have, let's say, the point of view of electric vehicle manufacturers on how they see the management of end-of-life batteries. An interesting question, in our opinion, is are they considering end-of-life batteries a cost, as maybe it's the situation now, but will it be a value in 5 or 10 years, considering the potential reuse and the potential market that could come from this opportunity of reuse in stationary application? And what are the actions that are they doing if they are developing something in terms of, as we discussed, in circularity by design, standardization, and having a more open access to the information that are stored inside the batteries, inside the battery management system in electric vehicles? That could be a significant step towards enabling this further opportunity of using of better using critical raw materials that are required for batteries. And that's all, I suppose. So thank you.
Thank you very much, Pasquale and Kamyap. So as I indicated at the beginning, we are going to be going through some of the questions that we have received in the chat section. So we have received a question from Tim Waker, who asks if second life batteries, can they compete economically with new batteries in stationary storage? And that's considering the cost of converting second use batteries. Pasquale or Kamyap would like to take this question?
Okay, let's say that for sure in this moment, it's hard to say that now they are convenient, because as I discussed, all the first projects that we are developing are more or less first of a kind, no? Because all of them, because of their innovative nature and also the willingness to explore new strategies, is somehow starting from scratch. So costs in this moment are elevated, not for the battery pack itself, but for everything related to the integration of the battery, and so all the engineering activities that are required to make the battery work in a different context. The projection of the cost per kilowatt hour of the packs are good, in the sense that there was a slide, I suppose, with some evaluation made by third-party analysts that indicate that second life batteries, in particular with the direct use approach, will be competitive in at least, let's say, in terms of cost per kilowatt hour DC side. Let me say, where we have to work, we, let's say, as an ecosystem of actors that are working with batteries, is on everything else. So not just on the battery itself, but on everything that can enable the use of second life batteries. So I repeat again, standardization, open access to info, to information of residual capacity, possibility to make them work with battery packs in series. So everything related to the certification that is required, a design that somehow helps the use in a stationary application. For sure, it's required to make not just the battery economic, but the battery system. So the battery and everything that goes with it to work in stationary conditions. So if all of these actions will be done by the various players, economical competitiveness could be reached.
Thank you, Pasquale. A second question, are you guys aware of any comparative study of the use of second life batteries with renewable energies and how they compare with the use of brand new batteries?
Well, let's say I think that more or less the previous answer, my previous answer answered partially, at least partially also to this question, in the sense that I'm not aware of, let's say, complete studies, because in this moment there are various approach possibles. So I'm not aware of specific comparative studies, at least publicly available. No, so for sure there is a literature about the technical possibilities, but I think that it will be required to have access to, let's say, to the information of the first pilots that are, let's say, that have been developed around the world to match not only, let's say, the upstream part of the project, so the cost, the activities that are required to make second life batteries work, but also to the second part, let's say, of the story, that is how the batteries, the second life batteries, perform for various in various applications, in various use cases, so with different cycling and pattern schemes. Now, I think these informations together will give a real comparative analysis that for sure will be useful to understand the potentialities of this application.
And before closing the webinar, we have one question for both of you. What would you recommend as further research works to improve the second life battery usage and to make it economically feasible?
Well, I don't know. Let's say if coming up as some suggestion from my point of view. Let's say also considering the experience that we as Enel are having on the demo, understanding better, let's say, the degradation model of a battery for sure is something that is interesting, because let's say still something that is not clear also for first life batteries now. So we have a lot of uncertainties also on first life batteries, how really degrades, because you know battery supplier typically provide end users with curves that are quite standardized for a typical application. So for example, 1 cycle per day with a certain temperature, with a certain depth of discharge. So really understanding how a battery behaves in times with a complex pattern, with different, let's say, external conditions, is something that is still open, is an open problem for stationary applications. And I believe that even more difficult is to define the degradation of a battery in an auto vehicle application in which the variability is even higher than in stationary applications. So for sure, anything that goes in the direction of really understanding how a battery performs and behave, not only, let's say, in the first part of its life, but towards the end of life, is an interesting approach. And then, of course, let's say more related to the, because this is something that is, let's say, more related to the chemistry of the battery. Going on the engineering world, everything that can support the integration. So, for example, I don't know, the world of DC-DC converters that could be required to match different residual voltages of the batteries with inverters is another interesting topics. Having a standardized BMS that could be accessible, let's say, for various users to extract information about let's say the residual value of the battery is another important approach. Building pack that can be used connected in series to work at higher voltages than the one that are typically used in electric vehicles. These are, let's say, something that comes to my mind that can help this world.
Sure, and maybe just to add, I think I agree 100% with Pasquale regarding the mechanisms of failure and degradation in batteries are very important. That we, first of all, we do not understand completely at this time. There is a whole chemistry of batteries. I mean, when people talk about lithium-ion batteries, there is NMC, there is LCO, there is LFP. There are so many different chemistries with their own failure mechanisms, and the difficulty is that when we talk about a battery has reached its 80% of retention, once it reaches that, the way or the history of the battery getting there has an influence on how it will behave later also. We know that when you ask high C rates and discharge and charge rate from the battery, actually it abuses so much the battery that the longevity of the battery depends on its history, actually, partly, not only on the manufacturer or the chemistry. So it's hard at this time just to go with one value of the state of charge or the state of health to say, okay, this battery can go to the second life or not. And I think there is a lot of work now being done on seeing how artificial intelligence also can help in learning about how to diagnose a battery and see where it should go. Is it worth it? There are some people actually to believe that even when you reach 80%, it's better to recycle it than to use it as a second life. That these are different scenarios that need to be looked at, and at this time actually it's not completely clear, but I think the kind of studies that are being done by colleagues is important to shed light on this.
Perfect. Thank you very much, Pasquale and Kamya, for your time on the presentation. On behalf of the Global Sustainable Electricity Partnership, I would like to thank you to all the participants that attended the webinar. The presentations in the 3 languages will be shared on our website. And again, thank you again for being with us this morning. Have a good day.
Thank you,
everyone. Thank you. Bye-bye.
Bye.